Hello there. Today we're going to talk about how do we graph transformations of parent functions. Well, the very first thing that we need to do is figure out what are all the parent functions. Here are four right here. Let's look at this very first one. This is called a constant function, and its equation is of the form y equals c, where c is just some constant, some number. The next is the identity function, or just a linear function. That's y equals x. That's whenever you get the straight line right through. Up next is, you guessed it, the quadratic, y equals x squared. That's a parabola. And then over here, that's the cubic function, y equals x cubed. So far, you should be pretty familiar with all of these, and you should also be able to describe their shape and their domains and ranges and things like that. All right. Up next is a function that we're still familiar with, the square root function, y equals square root of x, with a domain of 0 to infinity. Then, near the end of Algebra 2, you learned about the reciprocal function, y equals 1 over x, the parent function for rationals. And of course, I can't leave out the v-shaped absolute value function, the function that acts just like a linear, but then whenever it wants to go negative, boom, it bounces right back up into the positive y values. All right, and this last parent function I've actually decided we are just not going to worry about for today. I mentioned earlier describing the characteristics of a parent function, so on this slide I'm going to show you what I mean by that. So here I've listed out all the characteristics of f of x equals the square root of x. We have a domain and range, its intercepts, both x and y, here they happen to be the same, whether or not it's even or odd, where it's continuous or not continuous, its in behavior, and where it's increasing or decreasing, like which intervals. All right, let's do a little bit of a review from Algebra 2. Vertical translations of parent functions. That's whenever you have a plus k. So as you can see here, the green function is our parent function, f of x equals x squared. So what would this function be whenever it was translated up? Well, because the function moved up 3 units, I can call this new function, we'll give it a different name, g of x, is x squared plus 3. And all of the parent functions are going to behave this way if there's an outside number here. Now, of course, if this was minus, it would have moved down. But yeah, that's why I just leave this as f of x, because it represents all the parent functions. All right, horizontal translations, this h, these can be a little bit trickier because you have to pay attention that it's minus h. So whatever h is in here, its sign is actually different than what it appears. So we just have to remember that it'll move right when h is positive and left when h is negative. But think about it. If you put a negative h in here, you'd have x minus negative h, which would make it look like x plus h. All right, so let's try to write the equation of this black function here. We see that it has moved left 1, 2, 3, 4 units. So plugging in a negative 4 here would give me x minus negative 4, or g of x is equal to the square root of x plus 4. All right, so now let's talk about reflections. We're used to dealing with over the x-axis, but we're also going to talk about over the y-axis. All right, so to reflect over the x-axis, you just put the negative outside. G of x equals negative f of x. Here we have an example of that with the absolute value, f of x equals absolute value of x. And see, g of x, just putting this negative out here, flips the function over the x-axis. Now, notice that this negative is outside of the absolute value. What would happen if we put the negative inside the absolute value? Well, that's how you reflect over the y-axis. G of x equals f of negative x. Now here I can't use the absolute value again as an example because this has y-axis symmetry, but let's just look at a different one. Here the square root function is really a good example to look at because here's your f of x equals the square root of x, and then to reflect it over the y-axis, we just made the square root of negative x. Hopefully you're asking yourself, why does this work? I thought you can't take a square root of a negative. Well, that's why it has to go this way. The square root of negative 1 makes positive 1. All right, the next thing I want to talk about are vertical dilations. And you should remember that a dilation is whenever you can compress or shrink a function or expand or enlarge a function. And we can do this vertically or horizontally. So we're going to focus on vertically first, and that's whenever you have this a multiplying the function. All right, so f of x will be expanded vertically if the a is greater than 1, or it'll be compressed if a is between 0 and 1. We don't really include those negatives because we already talked about if it's negative, it just reflects. All right, so what do I mean to expand or compress vertically? Well, here's a function. And imagine that we could just grab this thing, since it's vertically, from the top and bottom, okay? And if we expanded it, this function would become skinnier. And if we compressed it vertically, this function would get wider. So let's see some examples of that. All right, so in this first example here, the blue function is f of x equals x squared, and the green function is f of x equals 2x squared. So we can see that 2, this a, is greater than 1, so we're going to get an expanded vertically. So it got skinnier. And what happened was all of the y values were multiplied by 2. And if you think about it, that should make sense. If you made a table of x squared, the last step would just be to multiply those y values by 2. So 1, 1 becomes 1, 2. And 2, 4 becomes 2, 8. Whereas here in this example where the a was less than 1, the graph got wider because it got squished down from the top and bottom. All the y values were multiplied by 1/2. Making the y values go up half as fast as this blue function. All right, lastly, we're looking at horizontal dilations. And this is whenever we're multiplying this x by some a. In this case, if a is greater than 1, you're going to have a compression horizontally. And if a is between 0 and 1, it'll expand horizontally. All right, so just like last time, whenever we were, expanding and compressing vertically, horizontally, it's as if we're grabbing the sides and expanding it horizontally or compressing it. And you should also take note that it's kind of counterintuitive. Like whenever a is bigger than 1, that's actually compression. And whenever a is between 0 and 1, that's an expansion. All right, so let's see what this looks like on a graph. All right, so here we have the red function is the parent, y equals x squared. The blue, see this is between 0 and 1 because it's 0.5, and it expanded horizontally. You can imagine grabbing each side and pulling it left and right. And then here where a was greater than 1, it's 2, that compresses horizontally. So from the sides it got pushed in to make this skinnier graph. But notice in this case, this is also just the same thing as 4x squared, which would be an expansion vertically. That's why the horizontal dilations, sometimes they're a little bit harder to see or to write from a graph. All right, so real quickly, let's try to list what transformations were applied to f of x. You can pause the video and then check your answers with mine here in a second, okay? I'm pausing in 3, 2, 1. All right, so in this first one, this was stretched vertically by a factor of 3, since the 3 is multiplying the function. Compressed vertically by 1/2 here. Now, whenever we had the 2 inside, this was compressed horizontally, right? We compress whenever this number is bigger than 1. Now this one was stretched vertically by a factor of 2, and it was also stretched horizontally by a factor of 3, because this is between 0 and 1. All right, and that's everything for parent functions. Bye.